Alright, ladies and gentlemen, today's class recording has started. So, you'll see the title of today's presentation is How Do We Get Charges to Do What We Want Them to Do? There are, in my estimation, two things or two units that we need to understand in order to understand electricity. One unit is atomic structure. You need to know about protons and electrons and different parts of the atom. The other unit is energy. And so I kind of mentioned this a bunch in the first semester. Energy is one of those things that we carry on throughout the entire year. It's a foundational idea of physical science, and we just talk about how it applies to different situations over and over again. So, starting off, what's our working definition of energy? The ability to do stuff, the ability to change things, the ability to make things different than they were before. So keeping that in mind, all right, let's take a look at a couple of situations. All right? So, for review, are we ready? The green part at the bottom is the Earth. The yellow is just an object. We'll call it a yellow ball, right? And the first thing we're going to do is we're going to do this. Okay? So, yeah, oh, sorry. I forgot to tell you, there's like some pretty cool animation today. Like, if you think that was cool, then just you wait. All right, so it's like the height of animation of Windows 2000. So, you know. So. All right, if we talk about energy, what happened to energy when I lifted the ball from the ground to a certain height in the air? Good. Gravitational potential energy increases. Did we do work on the ball? Yes, right? Work is a transfer of energy, right? Work causes the energy to change. The ball does not spontaneously move upward. Something has to be done to that ball to make it move upward. So work is done that increases the gravitational potential energy. And I think we know what happens next, right? If I let it go, what's going to happen? From an energy standpoint. Gravitational potential energy decreases, but then kinetic energy increases, right? So as we move downward, right, gravitational potential energy decreases, kinetic energy increases. Good? Is that we okay with that? No problem, right? All right. So keeping that in mind, remember yesterday at the end of class we introduced the concept of a field, okay? And a field is an area that surrounds an object where it can do things to other objects. All of this demonstration happens in which field? Earth's gravitational field, right? The area surrounding Earth where it can gravitationally affect other objects, right? We talked yesterday about field lines. Field lines, here I should do this. So hold on a second. Here. I really just want to do this because it was a sweet drawing and I'm pretty proud of myself, so I want to pull this drawing up again. This sweet drawing of the Earth that I did, and I was like so proud of it. So, right, the arrows represent the gravitational field lines. We said the field lines are representing what would happen to objects. So gravitational field lines always point towards the center of the Earth, right? Getting back to, not this, getting back to this, right? When we move the object this way, we're moving it up. But how are we moving it within the field? Are we moving it with the field or against the field? Against the field, right? And when we move it against the field, potential energy increased. If we let the field do its thing, what happens to potential energy? It decreases, and usually there's an increase in kinetic energy that goes along with it. Okay? All right. So, electric potential energy. So, Gravitational potential energy is based on what?
Gravity.
Gravity, yes. There's something else that it's based on.
Height.
Height or location, right? Gravitational potential energy is based on location in a gravitational field. What do you think electric potential energy is based on? Location in an electric field, all right? The energy of a particle due to its position within an electric field. And remember, right, energy, the ability to do stuff. So the ability of a particle to do something based on its position within an electric field. Okay? It's still energy of position, because that's what potential energy is, but now instead of a gravitational field, we're talking about an electric field, right? Electrical potential energy is a form of mechanical energy. We didn't talk about that when we first introduced the idea of mechanical energy, but it is, because like the three types of mechanical energy we talked about before, gravitational potential, elastic potential, and kinetic, we convert those three from one to the other, etc., etc. We'll throw electrical potential energy in there too, and we'll start converting that into other forms of energy, specifically kinetic energy, right? When a charged particle is moved within an electric field, work is done, and the energy of that particle changes. Just like when we move an object in the gravitational field, work is done, and that particle changes. Or the energy of that particle changes, okay? Ready? All right, so let's interpret this drawing. You have this drawing on your paper, right, and a couple questions that go along with it, okay? Here, let's say this is just an object that has a positive charge. This is just an object that has negative charge over on the right-hand side, okay? These arrows, the orange arrows that are in here, represent the electric field lines. Remember yesterday, we talked about that the electric field is based on what would happen to a positive charge, okay? Positive charges move away from other positive charges and towards negative charges. That's why the arrows run that way. Good so far?
Yeah.
All right. Let's say this yellow dot now represents just a single proton. A single proton that has a positive charge. Okay? This happens first. All right? What did I do there? Okay, went against the field. What's the end result of moving that positive charge against the field? Say again? It already has an imbalanced charge. Let's talk about it from an energy standpoint. If I move this positive charge against the field, Alex, what happens?
It has greater electric potential energy.
Perfect, right? In this spot here, I have increased the electrical potential energy. Okay? Hold on a second. We'll summarize all these things here in a second. Okay? So, does that happen on its own?
Nope.
No. What would I have to do to that proton to make that happen? Well, work, right? I have to do work on it. I have to apply a force and move it against the field. That's how I increase potential energy. But does this proton like being there?
Nope.
No. If I let it go, what's going to happen?
Come back.
It's going to move back. From an energy standpoint, what's going to happen? It loses what kind of energy? Electric potential, but if it's going to lose electric potential energy, what has to happen? It has to gain kinetic, right? So I move it this way, and, right, the electric potential energy decreases, and the kinetic energy would then increase, right? Does that make sense? Okay, so if we talk about three ways to increase electrical potential energy, you saw one way. If I move a positive closer to a positive, that's going to increase potential energy, right? Basically, what we have to do and Jack, you kind of threw this out there first, right? How do we have to move something in relation to the field? Against the field, right? So that's the key. There are three ways that we can do that, right? Oh, hold on. So, the first way we can do that is move positives closer to other positives, right? So now if we start answering this question, right, it says, what are three ways that electrical potential energy increase by changing position, right? The biggest thing that we have to keep in mind, and maybe you put a star next to this one first, is we have to move objects against the field, okay? The first way we can do that is move positives closer to other positives, all right? Hopefully, logically, you can figure out what the second one is. If we move negatives closer to other negatives, right? If we move something negatively charged towards something that also is negatively charged, right? That will increase the electrical potential energy too. What's a third way? We said we put things, positives don't like being close to other positives. Negative don't like being close to other negatives. What's a third way that we can increase electrical potential energy? Move them both. How would we move both of them? We could do that. That's actually the next question in the next picture that we're going to look at. So positives don't like being close to other positives. Negatives don't like being close to other negatives. What do positives and negatives want to do to each other? Attract. So they want to be close to each other. How could we increase potential energy? Separate them, right? If we move positives and negatives away from one another, that increases potential energy. Because what will they then want to do? Come back together, and that turns potential into kinetic. All right? Good there? Okay. Going back to this picture here, right? Sorry, we got those three things? We good with that?
Yeah.
Okay. All right. So, against the field, increase the potential energy, right? If it moves with the field, potential energy decreases, but kinetic energy increases, right? What if I move it that way? What if I move it perpendicular to the field? Have I moved positives closer to positives?
Nope.
Have I moved negatives closer to negatives?
Nope.
Nope, right? Have I made positives and negatives farther away? No, right? So, how can a positive charge move in a field without changing the electrical potential energy? How about perpendicular to the field? Or, Sammy, it's up and down in this picture, right? But maybe you think of it more as side to side, right? We can't do one of those three things that we just listed in the previous problem, right? The general answer is we're moving it perpendicular to the field, right? Because it doesn't change the position relative to other positives or negatives. Okay? Good there? So any changes in electrical potential energy there? No. Okay. All right. If we do any of these three things, right? Just to review the answer to the previous question, right? If we do any of those three things, positives closer to positives, negatives closer to negatives, or positives and negatives farther away, we increase the potential energy. Will any of those three things happen on their own? No. In order for those three things to happen, we have to do what? Apply force, and that means we have to do, from an energy standpoint, we have to do work to make these things happen. Okay? All right. Here. Next picture. Sammy, this gets a little bit more into what you were kind of going there, right? Same kind of setup, but in the picture on the left, right? 5 positives and 5 negatives on each charge plate. There's more than that, but for our purposes, right? But on the one on the right, 3 positives and 3 negatives. Stronger electric field, weaker electric field. More field lines, less field lines. Right? Which one's going to change the electrical potential energy more? The stronger field is going to change the electric potential energy more, right? Think about it with the gravitational field here versus the gravitational field on the moon, right? Which one has a stronger gravitational field, Earth or Moon? Earth has a stronger gravitational field. If we lift something up in... Is that okay? Oh, exactly. I thought somebody said Earth. If somebody said Earth, good. If you said Moon, I just corrected you to Earth, right? So, Earth has a stronger gravitational field, so if we lift something up to the same height on Earth versus the same height on the Moon, do more damage on the Earth than it does on the Moon, right? So, for the last question there on the page, right, there are 2 ways that electric potential energy can increase other than changing the position. What are they? One, you can increase the strength of the field, right? What's the other way? Mass doesn't play a role here, but what does play a role? Weight. Right? If that's a single proton, right, we move it left and right, it changes the energy, or it changes the potential energy. What if it's 2 protons? How much is the potential energy going to change? It's going to double. In fact, it is going to double because it is a direct relationship. So we can increase the field, or we can increase the charge that we're moving in the field. So we can increase the field strength, or we can increase the amount of charge we're moving in that field strength, right? Sammy, because you threw it out there just to make it parallel, right? That's the equivalent of increasing the gravitational field, moving from the moon to the Earth, or increasing the mass of the object that we're lifting up, right? Because gravity depends on mass. Gravitational potential energy depends on mass. Electrical potential energy depends on charge and field strength. Okay? Same idea, but now we're dealing with different things, right? Same, like the contributors are the same, but how we show them is different. Okay? Good there? All right. So let's talk about potential difference and voltage, which are 2 terms that are similar, not exactly the same, but as far as you're concerned, we're pretty much going to call them the same. Okay? All right. So the potential difference tells the ability of an electric field to change the electrical potential energy of a positive charge, or the difference in potential energy at different places in that electric field, right? Those 2 things are basically stating the same thing, just different ways, okay? What it comes down to when we're talking about voltage, and you'll hear me say this a bunch over the next couple of days, all right? When we discuss voltage, we're talking about energy, right? Voltage relates to the energy, and specifically the electric potential energy, okay? Voltage describes energy, specifically electric potential energy. Okay? Mathematically, we define or we measure the voltage in a unit called the volt. That's pretty convenient. All right? So we talk about it in 1 joule per 1 coulomb. So we talk about it in energy per charge. Does that make sense? Energy is measured in joules. Charge is measured in coulombs. So we're talking about changing the energy of a charge. Okay? But, more important for our understanding, we will not do many calculations with voltage, current, and resistance, right? We'll talk about it much more conceptually. But when we're talking about voltage, we talk about energy. That's what voltage describes, okay? Good? All right, let's take a look at this picture, okay? Here is a picture of a simple circuit, okay? We'll talk much more about circuits over the next couple of days, but like I said, this is the basis of what our society is built on, right? Our modern society is built on electricity and harnessing electrical potential energy to do the things that we want to do, all right? So you get a new toy. I don't know if you guys get toys anymore, but whatever, right? When you were a kid, you got a new toy, and the most disappointing thing was it was an electrical toy, but what does it not come with? Batteries, right? Okay. So let's talk about what a battery does. A battery, different types of batteries are measured in voltage. Batteries supply energy to the circuit. Okay? If you talk about batteries, like I said, batteries are coming in different voltages. The small round batteries that most of you guys use, like in whatever things at home, right? AA, AAA, C batteries, D batteries, those are all 1.5 volt batteries. The square batteries that you put in like the smoke detector and some other things, those are what? Those are 9 volt batteries, right? They're measured in voltage. Voltage relates to energy. Charges that pass through a 9 volt battery gain more energy than charges that pass through a 1.5 volt battery. The battery in a car battery, yes, right? Car batteries are 12 volts. Those things are huge, yes, right? Now, the size of the battery tells us something about it, but not the voltage, okay? We'll get into that a little bit more on Monday, all right? The size of the battery does have something to do with it, but it's not the voltage, okay? All the charges that pass through a 9 volt battery gain 9 volts of energy, right? Or per charge, 9 joules per charge, right? So, batteries supply energy, and the way to do that is through work, okay? Here's a battery down here at the bottom. Notice, you guys don't have this in your picture. I added this to my picture, but you might want to add this picture. I added a bunch of arrows through the battery. What do those arrows represent? Electric to the direction of the field. Okay? And, like we said, right? The field is determined by what would happen to a positive charge. Positive charges would move away from the positive terminal of the battery, and towards the negative terminal of the battery. Okay? However, what moves around in a circuit? Electrons move around in a circuit, right? So even though, right, okay, there is a field inside the battery, and watch this sweet animation, ready? Okay, so here's an electron, and it moves that way. Even though it's moving with the arrows, it's moving against the field, because the field tells what should happen to a positive charge, but that's a negative charge, all right? Are we okay with that? If we think about it in terms of the battery, electrons don't want to be at the negative terminal of the battery, right? They want to be over there. They'll only move through the battery towards the negative terminal if we do what? No. What do we have to do to make things move against the field? We have to do work. Batteries do work on electrons to increase their electrical potential energy. Okay? Now, how they do that, don't worry about that. That's not part of your chapter right now, okay? That gets into electrochemistry and all kinds of like chemical reactions occur. But the gist of it is batteries do work on electrons to increase their potential energy. All right? See these little see no. We're gonna make a loop. All right? Okay? So, see these little boxes? These little boxes are going to show up along the way as we go along. Okay? All right. So, batteries do work. Increase the electrical potential energy of the charge. But, the whole story of energy basically is we increase the potential energy and then do what with it? By turning it into kinetic, right? So, the battery does work and moves these charges over to the negative terminal. What do the charges then do? Kinetic energy is based on what? Movement. So now charges start to move. All right? Ready? Here we go. Here's the first step in the process. And pay no attention to this little jump right here. Okay, ready? Here it goes. Okay. I should move this out of here. Okay. And that's okay. Switches are just conductors. That's all. Right? So, as electrons move within the wire, electrical potential energy is turned into kinetic energy. Charges start to move. And as you can see from the picture, right, direction of electron flow. It's moving away from the negative terminal of the battery and making its way back towards the positive terminal of the battery. Okay? Good there? Here's where we start putting electrical components in our circuit. Okay? It's great to have these charges just moving through the wire. Sure, that's great, but that's not really doing anything for us. Right? Here's where we start doing things. Ready? This is kind of a long one. All right. Oh, I gotta go back here. Ready? Here we go. As electrons travel through the bulb, right? The light bulb, or as it's labeled in the circuit here, the load, turns electrical potential energy into light and heat. All of our demonstrations with gravitational potential energy turn potential into kinetic, but light bulbs turn potential into light and heat, right? Just like when we move, and we go there, right? It has something to do with friction, but we won't get into that. Finally, where do these charges end back up? The battery. What part of the battery, though? Positive terminal of the battery. We have moved a negative electron back close to the positive terminal of the battery. Does it have potential energy there? No. It likes being there, right? That's where it wants to end up. By the time that electron moves through the entire circuit, all of the potential energy that it gained by moving through the battery originally has been turned either into kinetic energy of movement, or light, or heat. Or, depending on what's in your circuit, it could have turned it into more kinetic energy, like if it's in a remote control car, right? It turns it into kinetic energy of the car. If it's part of a speaker, it could turn it into sound energy. Something. It has to turn electrical potential energy into other forms. When these charges get back to the positive terminal of the battery, they don't have any more potential energy. So what does the battery then do?
Do it again. Put them against the field.
What does it do first? It does what? Puts them against the field by doing work. It does work on those charges, increases their potential energy again, and sends them back out to do what they did before. Okay? Good there? All right. Don't forget, I will add the quiz for the first part of this unit up later today. It'll be due on Tuesday, and then we'll continue on with this outline on Monday. Have a good weekend, everybody.